Hello, good evening everyone. My name is Akhil. Today is our last session for the course Machinery Fault Diagnosis and Signal Processing. Similar to last week, this week also I will cover multiple questions from the entire syllabus. And yeah, you can find these videos uploaded in YouTube under the playlist name Machinery Fault Diagnosis and Signal Processing, Jan to May 2023 live sessions. Okay, so let's begin the first question for today. So the first question is, what are the objectives of uh, FMECA? The options are identification of potential failure, evaluation of the severity of failure, or both A and B, or none. So FMECA actually stands for failure mode effects and criticality analysis. So as in the full form itself, you can see failure mode effects and criticality, how severe they are and the mode of the failure. So the identification of the failure and how severe or critical it would be, all of this fall under failure mode effects and criticality analysis. So this is the methodology which industries use to identify and analyze all the possible or potential failure modes and how they affect the system, basically their severity and other cases, and also how to avoid such failures. Or mitigate the impact. Okay, so the options identification of potential failure and evaluation of severity of failures both will come under the failure mode effects and criticality analysis. So the option is C, A and B. Okay, so these are the primary objectives: to identify the potential failure and evaluate the severity of the failure, and then on how to avoid the failures or mitigate the impact of the possible failures. So these are the main objectives of FMEC. Okay, so let's move to the second question. The failure rate is high in the infant mortality zone of the bathtub curve because of installation defects, wrong or original equipment manufacturer specification, unfamiliarity of machine operator, all that. So in the bathtub curve, where the failure probability of the failure versus time of operation, there. So this is the bathtub curve where the potential failure probability of potential failure is initially very high. After that, it actually reduces and then stays almost same, and at the end of the time life cycle also it is again high. So in the initial stages, this is the infant mortality zone. So here the failure rate probably will be higher because if the it is not installed properly or the specifications are wrong. So when you are actually installing, you need to take care of whether the correct current supply is given, the correct airflow is there in the room, all these things. And if the machine operator is unfamiliar with it, so all of this usually happen in the initial stages, initial usage of the equipment. So they fall under the infant mortality zone. So all this actually cause the high failure rate in the initial usage of the equipment. So once these are all fixed, then the failure rate will be pretty low and the machine will work without any maintenance. And at the end of the life cycle of the machine, again due to the fatigue, wear and tear, the failure rate will be again higher. Okay. So the failure rate is high in the infant mortality zone of the bathtub curve because of the installation defects, wrong original equipment manufacturer specification, and familiarity of the machine operator. All these are possible. Okay, let's move to the next question. So how can you optimize the machine availability? By increasing uptime plus downtime, or increasing downtime or decreasing downtime, or none. So how can we optimize the or improve the machine availability? So what exactly is machine availability? Is the uptime by ratio of uptime by the total time. So uptime plus downtime. So if you want to improve availability, then if you decrease the downtime, then the denominator reduces. So the total fraction will increase. So availability improves by decreasing the downtime. Okay. So the answer is decreasing downtime to improve the or optimize the machine availability. Okay. Let's move to the next question. At resonance condition, the forcing frequency is equal to infinity, zero, natural frequency can't say. So when you are doing any forced vibration or there is a vibrating system and there is an external force, and if that external force, the frequency is equal to the natural frequency of the system, then the amplitude of oscillations would be very high. So that condition is called resonance, and that happens when forcing frequency is equal to the natural frequency. So at resonance, the forcing frequency is equal to the natural frequency into high amplitudes. Okay, so this is the resonance condition. Okay, so let's move to the next question. The critical damping coefficient in Newton per meter per second provided, or the critical damping coefficient provided that m is equal to 10 kgs, omega n is equal to 10 radians per second is. So you have to find the critical damping coefficient, the mass is given and the natural frequency is given. So what will be the critical damping coefficient when you know only the mass and the natural frequency? So this we have discussed in our earlier classes. So the critical damping coefficient is 2m omega n when you know the mass and the natural frequency. Okay, so this is actually 2 root km, but since omega n is root k by m, we can write k is omega n square into m. So using this, 2m omega n also gives you the critical damping coefficient. Okay, so in this case we know the mass is 10 kgs and omega n is 10 radians per second. So the critical damping coefficients would be 200. Okay, so this is how you can calculate the critical damping coefficient when only the mass and natural frequency is given. Okay, let's move to the next question. If the damping factor at resonance is 0.25, what will be the magnification factor? The options are 1, 2.5 and 0.25. So we are given damping factor and we are supposed to find the magnification factor. So if you remember our earlier weeks, we had a direct formula for the magnification factor. So using that formula we can estimate, but there is one more detail in the question that you need to carefully see. So how can we actually get the magnification factor? One by root over 1 minus r square whole square plus whole square. So this is the magnification factor formula. Now R is the ratio of the frequency to the natural frequency. So here they didn't give the actual frequency, but they mentioned resonance. That means R is 1. That means the frequency of excitation and the natural frequency are equal, and we are at resonance, so R is 1. And the damping factor is 0.25. So if you substitute these two values, magnification factor m is equal to root over 1 minus 1 0, so 0 plus 2 into zeta is 0.25 into 1 whole square. So 1 by whole square you can cancel out, 2 by 0.25, so 1 by 0.5, the magnification factor would be 2. Okay, so this is how you can estimate damping magnification factor if the damping factor is given. So in the case if the resonance is not mentioned, then they might mention the natural frequency and the forced frequency, or they can also mention forced frequency and Km, so that you can estimate the natural frequency on your own. Okay, so at resonance case we can directly write this as 1 by r is 1, so square root cancel 1 by 2 zeta for the case of r equal to 1. Okay. Just 1 by 2 into damping factor will give you the magnification factor. Okay, let's move to the next question. So you were given the stiffness and mass of a primary vibrating system as 2000 Newton per meter and 20 kg, and you are designing a tuned mass damper. What should be the natural frequency if you are designing a tuned mass damper? So that is the question, and you are given the primary vibrating system's stiffness and mass. So that means you can estimate the frequency of the primary vibrating system, natural frequency. So for the primary system, what should be the natural frequency? Root k by m of the primary system. So this gives us 2000 by 20. Okay, now we estimated the natural frequency of the primary vibrating system. Then if you are designing a tuned mass damper, what is the main condition? The natural frequency of the design system, secondary system, should be same as the natural frequency of the primary system. So that is the importance of the, or that is the design condition for the tuned mass damper. So the natural frequency of the tuned mass damper of the would also be 10 radians per second. Okay. So this is the important condition in the case of tuned mass damper. Natural frequency should be same. Okay, let's move to the next question. Which parameter represents the shape of distribution of data? Form factor, crest factor, skewness, kurtosis. The answer is skewness. Kurtosis talks about the tail of the data. So, how strong the tail is, or how heavy or light the tail is. Skewness talks about the asymmetric distribution of data. So, this actually talks about the shape of the data. So, either the data, so let's say you have a normal distribution, and if the data is skewed to the right or skewed to the left. So, skewness talks about the degree of asymmetry. So, it is the one which actually talks about the shape of distribution of data. Okay. Let's move to the next question. So, what should be the form factor of a signal? 5 sine 20 pi t. What is the formula for the form factor? RMS by mean, right? So, because in sine 20 pi t there will be positive and negative side, we will only consider the positive side for the mean absolute values. So, if you do that, when you have a sinusoidal wave, the RMS would be amplitude by root 2, and the mean absolute values, mean of absolute would be 2a by pi. Okay. So, this gives us 1 by root 2 this gives pi by 2 root 2 as the form factor. Okay. So, the form factor in a sinusoidal case is independent of the amplitude or the frequency, it's just pi by 2 root 2. Okay. What about the crest factor? Crest factor would be maximum by RMS. So, maximum is a by root 2. So, it will be root 2. Okay. Well, let's move to the next question. So if a positive DC offset is given to a time domain signal, its variance increases, decreases, remains same, can't say. So let's say you have the data x1 to xn. So if you are adding a positive offset, then that means your data would be x1 plus delta, so on. So when you do that, the mean would also add, for the mean also it would change by delta. So when you're actually doing the variance, which you need to calculate of this form, then the difference is added for the mean also. So the difference would become, it would be same as the original xi minus x bar. Okay, so the variance doesn't change. Variance or standard deviation don't change by adding a positive or negative offset to the all the values. So they remain same. Okay. Let's move to the next question. So what should be the bit frequency when the signals with frequencies 250 and 254 hertz are in the system? So what should be the bit frequency when your two frequencies are given? So the beating frequency is just the absolute difference between the two frequencies. So 250 minus 254 is 4 hertz. Okay, it's as simple as that. This is the beat frequency when you mix two signals whose frequencies are very close. Okay, let's move to the next question. To develop the envelope of a time domain signal, what is the technique that is used? 50 Hilbert transform, short time Fourier transform or subsystem analysis. So which will give us the envelope of a time domain signal. So envelope basically means let's say you have a signal like this. The envelope the signal would look something like this. So which transform gives us the envelope? So you can get the envelope by doing the Hilbert transform of the time domain signal. Fourier transform gives us the frequency. Short term Fourier transform also, if there is a non-stationary signal varying frequencies, that, and subsystem analysis doesn't give us the envelope. So the answer is Hilbert transform. This is the one through which you can get the envelope of a given signal. Okay, let's move to the next question. So inadequate sampling frequencies can lead to which type of error? Aliasing, leakage, quantization, or none of these three? What will happen when the sampling frequency is smaller than what it should be or lower than what it should be? So when you have a very lower sampling frequency, then a high frequency signal can be will look like a low frequency signal. So this is called aliasing. So a high frequency signal may look like a low frequency one due to inadequate sampling frequency, and that is why it's called aliasing error. Okay, and the leakage error comes because no windowing function applied while computing f. So if you don't have any window function, the data can suddenly have these jerks. So because of that, you will have something called leakage error. And quantization actually happens because of inadequate resolution. The data storage system. Okay. So in this case, inadequate sampling frequency actually causes the aliasing error. Okay. Okay, let's move to the next question. So initially you have stored it in an 8-bit memory card. Suppose the signal data is stored in a binary 8-bit memory card with the signal range being fixed same as before. If you store the same data with a 16-bit memory card, the new resolution will be how many times the old resolution. So what is the resolution formula if you have based on the storage and a fixed range? So from that we can estimate this. So old resolution is range by 2 power n being 2 power 8. New resolution is range by 2 power 16, right? Now this you can write as, right? So I divided 16 as 8 plus 8, so 2 power 8 into 2 power 8. So range by 2 power 8, we know old resolution by 2 power 8. So this is 2 power minus 8 times the old resolution. Okay, so answer is 2 power minus 8. So when you change the type of storage system, you will get such higher resolution. So 2 power minus 8 times the old resolution. If you go from 8-bit memory card to a 16-bit memory card. Okay. Let's move to the next question. So a voltage signal of dynamic range of 10 volts is sampled at 100 samples per second using a 10-bit analog to digital converter. What would be the amplitude resolution? So what is the formula for the resolution? Range by 2 power n, right? So what is the range here? It's 10 volts given, and the storage is n is 10, so 2 power 10. Okay, so 1024. So this is almost 0.01. So here this samples per second, the sampling frequency doesn't influence the amplitude resolution. You need only the range and the type of storage. Okay. Let's move to the next question. So you have a electrocardiogram signal with useful frequencies up to 120 hertz, and we are sampling this at 300 samples per second. What is the highest frequency that can be represented uniquely at this sampling rate? So first of all, if you have useful frequencies up to 120 hertz, what is the actual frequency necessary to each actual sampling rate that is necessary to track up to 120 hertz? So if you want to track up to 120 hertz, then you need a sampling rate of 2 into 120 hertz. So 240 hertz is enough. But you are sampling at 300 hertz, 300 samples per second. So if you are sampling at 300 samples per second, then what is the maximum frequency that you can get? Yes, 300 by 2 equal to 150 hertz, because you are sampling at 300 samples per second. So anything up to 150 hertz you can actually uniquely define. So the answer here is 150 hertz. So yeah, just even though you have only till 120 hertz, you are actually using a slightly higher sampling rate so that you can get even before better frequencies in the worst case scenarios. Okay. So because we have only 120 hertz, 240 samples per second is enough sampling rate. But since you are doing at 300 samples per second, any frequencies up to 150 hertz you can clearly uniquely represent. I hope that is clear. Okay, let's move to the next question. Determine the dynamic range of a transducer which can measure a bipolar signal of amplitude 10 volts provided that amplitude resolution is 1.25 millivolt. So if you have a resolution of only 1.25 millivolts but a total range of 10 volts, what would be the dynamic range? What should be the dynamic range? What's the formula for the dynamic range? 20 log 10 range by resolution. Okay, so 20 log 10, what is the range? 10 volts by resolution 1.25 millivolt. Okay, amplitude 10 volts and a bipolar signal, so the range would actually be 20 volts. Okay, So this would actually be 16,000. So most so you can write it as 20 log 10 16 plus, so this would be 3 plus log 10 of 16. So this would almost 84 decibels. So this is the dynamic range. Okay, the answer is 84 decibels. So usually this is also can be written as 20 log 10 maximum range by minimum measurement possible. So in most of the cases minimum measurement is the resolution. The answer is 84 decibels. I hope this is clear. Okay, let's move to the next question. So the following physical parameter is measured by using piezoelectric crystals: wind speed, force, temperature, current. So which of the following can be exactly measured by piezoelectric crystals directly? Piezoelectric crystals are actually designed to measure the force. Okay. Not the wind speed or temperature or current. Temperature you have a thermocouple or IR camera. Current you have all effect sensor. Okay. So it's not force is measured using piezoelectric crystals. Which of the following can be measured using stroboscope? Stroboscope is actually used to measure the rotational speed. So if it is similar to if the frame rate of the camera matches the frame rate of some rotating object, that object feels stationary. So that is the main principle which the stroboscope is works on, and it is used to measure the rotational speed of an object. Okay. Okay, let's move to the next question. So what is the reference power for air while calculating sound power level in decibels? While calculating sound power level SWL, what is the reference power? The reference power used is 1 picowatt, 10 power minus 12 watt for SWL. Okay. For sound pressure level, the reference is for SPL, the reference used is 20 micropascals. For sound power level, the reference is 1 picowatt or 10 power minus 12 watt. And for sound intensity level, the reference used is 1 picowatt per meter square or 10 power minus 12 watt per meter square. Okay. So these are the reference powers, reference levels used in different measures of sound intensity. So in the case of sound power level, it is 1 picowatt or 10 power minus 12 watt. Okay. Let's move to the next question. So when you have two sound pressure levels, 30 dB and 30 dB each, what will be the sum of the two pressure levels? when both of them are acting on this one source 2 and this one is giving 30 dB and this one is giving 30 dB. So at this point what would be the effective pressure level? So that is the question. So there is a direct formula for this which we derived and discussed in week 7's lecture, I think, March 13th. So what is that formula? So how many ever sound pressure levels you are adding up? The formula is 10 log 10 sum of 10 power SPL I by 10. So this way you can add how many ever sound pressure levels are there. Now if all of them are equal, if you have only two of them, then this would become okay. Now if the case where both are equal, then also we have derived that formula. Two into 10 power SPL by 10. So this actually comes out to be SPL 1 plus 3. Okay. So because of this, now you can write 30 plus 3 is 33 decibels. So we have actually derived this in that corresponding week. So if you look at it, then you will get the idea. Okay. So this is the answer here, 33 decibels. So when both are equal, you can just do this instead of doing all that 10 log 10 and all that calculations. You can just add the corresponding SPL given plus 3. Then only in the case when both the SPLs you are adding are equal. Okay. Okay, let's move to the next question. So sound waves with a frequency about 20 kilohertz are known as audible, ultrasonic, infrasonic. So the audible range for humans is actually 20 hertz to 20 kilohertz, and ultrasonic is the range above which we cannot hear, so greater than 20 kilohertz. and infrasonic is less than 20 hertz, the frequency below which we can't hear. Okay, so the answer for this case is ultrasonic. Okay, so the audible frequencies for humans are 20 hertz to 20 kilohertz. Above that are called ultrasonic, below that range is called infrasonic. Let's move to the next question. An unbalanced force can induce additional load on the bearings and leads to premature failure of the bearings on rotating shafts. True or false? So what do you guys think? Will unbalanced force don't cause additional load on the bearings? It does cause additional load on the bearings and it can lead to premature failure. So the answer is actually true. So that's why it is important to actually balance out the forces. Okay, let's move to the next question. In a rotating machine, an unbalanced mass m exists. It has an eccentricity e and rotates at a speed of omega radians per second. Determine the magnitude of the unbalanced force. So in this course, what is the actual reason for the generation of unbalanced force in a rotating machine when you have an unbalanced force? So the actual reason is the forming of centrifugal force is the generation of centrifugal force, an unbalanced centrifugal force due to this mass, and it's rotating at an omega speed. So what is the actual formula for centrifugal force? So it's mvr or mr omega square. So here the mass is m, the radius is actually the eccentricity e here, and omega square. Okay, so this is the unbalanced force, so it would be mu omega square. Okay, I hope this is clear. Okay, let's move to the next question. Identify the bearing that works on the principle of hydrodynamic lubrication. So hydrodynamic lubrication, so to the fluids. So which bearing works on that principle? In these four types of bearings we have. So magnetic bearing, as in the name, it uses some magnetic principle. Ball bearings use because rolling friction is much lesser than the normal static friction. Anti-friction bearings, as in the name, friction they use. The answer is journal bearings. They have fluid in between them, which works on the principle of hydrodynamic lubrication. Okay, the answer is journal bearing. Okay, let's move to the next question. What would be the vane pass frequency at the 1500 rpm for a pimp impeller having 30 vanes? So what should be the vane pass frequency? This we have discussed I think last week also and in the previous weeks. There's a direct formula for this. What's the formula? Vane pass frequency is equal to the rpm by basically the speed, rotational speed in radians per second, into number of vanes. So first we need to convert rotational speed in rpm to this. So 1500 by 60 rotations per second, sorry, into number of vanes is 30. So this would give us 750 hertz. Okay, so that is the answer for the vane pass frequency. Okay, let's move to the next question. So the phenomena of formation and collapsing of bubbles in fluid missions is called condensation, cavitation, capillary action, or convection. Formation and collapsing of bubbles in fluid missions. It's called cavitation. So when you actually have high flow rates at delivery, results in very low pressure at the inlet. So this forms bubbles which will burst again when they reach normal pressure zones. So basically at the inlet walls. So this bursting actually can damage the walls. So this is called the cavitation. Okay. This will also look like high frequency vibrations in the If you record the vibrations, then there will be very high frequency vibrations. Okay, this is a cavitation. The phenomenon of formation and collapsing of bubbles in fluid motion is called cavitation. Okay, let's move to the next question. So what should be the gear mesh frequency when you have a gear of 30 teeth rotating at 500 rpm? So this also we have discussed in earlier weeks. What's the formula for the gear mesh frequency? So number of teeth, this is similar to the vane pass frequency, and rotations per second. So 30 into 1500 by 60. Well, I can get 750 hertz as the gear mesh frequency. Okay, so this is also very similar to the vane pass frequency, but here it's the tooth that are going one after the other. Okay, let's move to the next question. So what should be the engine fairing frequency for a two-stroke four-cylinder engine when the output shaft is rotating at 1800 rpm? So this is also a question which we discussed in the previous week and previous weeks. So I'll give you a minute to try to find the answer and then I'll explain it. Okay, the engine firing frequency as the speed in rotations per second to 1 by k into number of cylinders. So this is the number of cylinders and k is 1 for two-stroke engine, 2 for four-stroke engine. So here it would be rpm is 1800 by 60. It's given as a two-stroke engine and 4 cylinders. Okay. Answer is 120 hertz. Okay, this is the engine firing frequency. This is the formula you can remember for estimating the engine firing frequency based on the strokes and cylinders in the output shaft RPM. Okay. Let's move to the next question. The vibration characteristic frequency indicating an oil whirl would be basically same as the rotating speed or 1.5 times the rotating speed. Point 0.6 to 0.7 times the rotating speed. Point 0.42 to 0.48 times the rotating speed. So what should be the vibration characteristic frequency that indicates an oil whirl? So when you have an oil well searching around in the chamber, you will actually get frequencies that are lower than the half of the rotational speed, because you would get the frequency is lower than the rotating speed, so it's usually around 0.42 to 0.48 times, which will indicate the oil well. Okay. So if this is actually equal to the natural frequency, then this would turn to oil whip and can cause catastrophic failures. Okay, so should be careful while doing the design. 0.42 to 0.48 times the rotational speed. Okay, let's move to the next question. So which of the below is a fault due to change in position of the minimum air gap between rotor and stator? So when you have a minimum air gap between rotor and stator, if that air gap is fixed or the position of the minimum air gap is fixed, then it is static eccentricity. Then it would be static eccentricity, and if it is changing, then it would be a dynamic eccentricity, because the eccentricity is actually kept on changing the position, so it's a dynamic eccentricity. Okay, so if you have a minimum air gap, the position, the location of the minimum air gap. So in case 1, to begin with, this is the location of the minimum air gap. So if it actually changes to, so if it actually changes during the operation, let's say from here to here, then this changing minimum air gap is the dynamic eccentricity. Okay, so now the air gap won't be here and it would be on that location. Okay, so this is the static and dynamic eccentricities. Okay, so let's move to the next question. Which fault detection technique is best suitable for the submersible pumps? Vibration monitoring, motor current signature analysis, oil analysis. So to actually do the vibration monitoring, you need accelerometer and the sensors. So keeping them in a submersible situation is not ideal. Thermography is not useful because the oil or the submersible leak water can take away the temperature based on convection. So thermography won't be suitable. Because it's submersible, oil analysis might also be not a great idea. So actually motor current signature analysis is best suitable for the submersible pumps because the control panel where current is supplied to motor will be accessible. The current, so by tracking this current or by analyzing current, we can identify the faults. Okay, so motor current signature analysis is best suitable for the submersible pumps. Let's move to the next question. So if you have a supplement frequency of 50 Hz and the motor is running at 49 Hz with the presence of eccentricity, current spectrum shows side bands at which of the following frequencies? At eccentricity. Okay. So when you have eccentricity, the side bands usually occur at Fs minus Fm and Fs plus Fm frequencies. So it would be 50 minus 49 and 50 plus 49, so 1 Hertz and 99 Hertz. Okay, so this is where the sidebands would occur in the case of eccentricity during the current spectrum analysis for a motor. Okay. Let's move to the next question. Lubricating oil in machines perform which are the following functions? Minimizing wear in moving parts, help in keeping parts cool, washes and carries away dirt, all of above. So when you have a lubricating oil, you reduce the wear between moving parts because now the oil will be in between those two moving parts and it reduces the friction, so which then reduces the wear. So it reduces the wear, help in keeping parts cool. Because there is oil everywhere, oil takes has with due to convection it can take away the heat from the parts better than just air, so it can keep the parts cool. And because oil is actually flowing, if there is any wear and parts or any dirt gets created, that actually gets cleaned away because of the moving oil. So it actually performs all the above operations. The answer is all of above. Lubricating oil in machines perform minimizing wear, helps in keeping parts cool, and washes and carrying away dirt. So because of this, you can actually do oil analysis to characterize the faults in a machine also. Okay, let's move to the next question. So in which of the following tests capillary action principle is used? So which this we discussed in the current week actually. So in the dye penetration test, where you use a dye to see the extent of the surface cracks. So in this, the dye actually goes inside the cracks because of the capillary action. Okay, so it is a dye penetrant test. Okay, so this is it for this week, and this is the last session for the course. And hope you gained are able to solve assignments better because of these sessions. And your exam will be in 2 weeks, I guess. And thank you for attending these sessions. And hope you do well in your exam. All the best to your exam, and all the best to your future also. Goodbye.